Good morning, everybody. Welcome to this session. Thank you all for attending, and thanks to MLOps for arranging such a wonderful event. My name is Kaushik Roy, and I have more than a decade of experience in machine learning deployments. Currently, I'm rendering my services for the government. So what is my goal here today? My goal here is to introduce you to the concept of location data and what are the things you can do with that data, right? And to do that, we will begin with a question. The question is, are your models location smart? That means, have you factored in the location of a particular event in your models? So let's see the roadmap that you are going to take. So this is how the concept is laid out. First, we are going to look at some terminologies, some contributors in this space, and then we are going to go into some of the topics that is used in analysis. Finally, we are going to summarize the knowledge that we gain here and maybe take some few questions after this, right? Great. So the first thing we have to talk about is multidimensional thinking. Multidimensional thinking is something that all data scientists have to do at some point of time, right? So we begin with the model. What is a model? A model is a function that is derived from the data, right? So hence the term data driven. Now, what does the model need? The model needs dimensions. You can give different kinds of input features. You can give event related features or entity related features, and you can put time related features. You can also put location related features. And location related features are derived from location data, which is very expensive. So you might want to know how to deal with that before you go on to do these things. Once you have location data, you apply the first law of geography, which states everything is related to everything else, but near things are more related than distant things. This is this is called Tobler's law, and this basically means that proximity of the events and the distance between them can have some signals actually, right? So let's see how that works. Also, we will be introducing we will be working with heterogeneity. So just like you have heterogeneity in other kind of data, you will have heterogeneity in spatial data, right? We will also see things like autocorrelation and autoregression, which are actually borrowed from time series time series or econometrics. Also, if you're doing multidimensional thinking, being a bit of a polymath actually helps because if you have knowledge from different domains, you can actually make good models. Also, you need to have a way to do hyperparameter tuning because there are some hyperparameters here. And you need to have a prediction API where you will predict for new data, right? Also, there are a lot of open source projects that are there and a lot of proprietary softwares also. If you're having any kind of experiments or exploration, please make sure that you test the significance of that before you do all these analyses, because it will have a dollar value attached to it. So, body of knowledge. So, what is a body of knowledge? A lot of people in the industry actually know what a BOK is. A BOK is more than simply a collection of terms. A BOK is like a knowledge representation. It's the list of competencies that you need to be good at something, right? So, who are the biggest contributors of the spatial BOK? Well, all these spatial analysis started actually during World War II. And after that, a lot of private organizations have come into play. So we have governments with open data policies like Canada, UK, Australia, and the US. And then we have private enterprises like Esri and Hexagon, who are actually big contributors themselves. Also, so that data scientists and private and public are interoperable, we have Open Geospatial Consortium, which is the gold standard for geospatial data. We have ISO 211 to take care of the semantic mapping, so you can use knowledge graphs in your geospatial data. So these are the list of competencies that you need to actually be good at this. Now you will see that there is something for everybody here. There is something for data scientists, there is something for business analysts, and there is something for data engineers. And that's the whole point of it. The point is that these teams have to collaborate and interoperate between themselves. Now, this is only just a small list of the actual list of competencies, of course, but these are the things that you need there. So we start with data visualization. Data visualization is an important part of all data scientists, right? The first thing we do is data visualization. And in terms of geospatial data, data visualization is actually called as cartography because of maps and stuff, because the primary form of visualization is maps. Now, the more interactive the map is, the more insights you will actually get out of that. So you can see that there is something called a cartography cube, where you have visualization and you have communication. Also, cartographic visualizations are kind of sensitive because it deals directly with land and like property. So there are three axes of operations. These are called epistemologies. So one is science, because geospatial data is totally scientific. It is also art, because we are doing a lot of things that we could not do before. And you have to have good ethical practices, because along with these things, there is the data scientist who is bringing in the human intuition, and according to his experience or his thoughts, he will either be doing idealistic analysis, which is like making the perfect maps, making a generalized truth maps. The data scientist could also be doing humanistic analysis, which is kind of making things into context and making different kinds of trade-offs to solve a business case. One very interesting application of cartography is subversive analysis, where it is actually beneath the cartography and you distort the truths, because maps are so powerful things, powerful visualizations. If you do minor distortions, it is very difficult to notice. So you have to use good visual variables, and you have to be very ethical when you're visualizing these maps. Otherwise, you'll end up doing a lot of damage. For example, you might have heard about gerrymandering and all these concepts. So what are the top 10 visuals that we have in geospatial data? The first visual we have is point maps. Point maps are just plotting points on the map. Here you can right away see that North America and Europe are the biggest contributors in Wikipedia, right? The other kind of map is flow maps. Flow maps actually tell you from where to where, if there is traffic flowing, if there is a pattern of disease that is flowing, any kind of movement is shown by a flow map. So there is hexbin map, which divides the entire map into equi-sized hexagons and then colors them based on some attribute, right? There is the line map, which is used to map road networks and rivers and different kinds of logistic networks, transportation. The choropleth map. The choropleth map is a kind of an aggregate view that shows the distribution of spatial variables across the area. So you can see that the colors actually represent the density of points in the area. There is the heat map, which actually shows you concentration of points in certain areas, and people do a lot of analysis as to where events are clustered around. The bubble map actually uses different sizes of bubbles or rounds to measure different objects. For example, you can have 5% as a small bubble and then 20% as a bigger bubble. And you have cluster maps, where you just get a representation of the cluster and the number of points that are there in it. So it quickly tells you how many points are there in that particular cluster. There is also the cartogram map. The cartogram map actually distorts the actual boundaries of the map and then uses that distortion as a representation of a number. So you can see that the map is a little distorted here. That's because it's actually a proportion of the votes that are there. Isochrone map. This is very interesting. And we are going to talk about this later. So isochrone map starts from a point and maps out where you can reach using a certain mode of communication. So you start from a particular point and then you move out using some modes like driving, walking, or bicycling, and see what are the places that you can reach. Height maps. Height maps uses a 3D representation. It just gives you another axis to do your thing, to represent your number, just another visual variable. And finally, spatiotemporal maps, which actually uses the same geographical maps, but spanned out in time. So you'll have the same place map in different points in time. So you have different ways to visualize this data. You have open source projects, you have closed source projects, and these are actually proprietary projects. Kepler.gl is a tool from Uber. It's a very good mapping tool. D3.js is the de facto standard for generating visuals. QGIS is a very interesting desktop application that does a lot of spatial analysis. And leaflet is again a JavaScript-based library you can use in Python. So now we come to the data engineering. So to do data engineering, we actually need to understand how geospatial data is encoded, right? We will have file formats, we will have different kinds of softwares that can do this. So to understand or to encode geospatial data, we actually do that in 3 ways. So one is the vector data, then you have raster, and then you have triangular irregular networks. Vector data is actually points and lines and polygons. So you can say there's a river there, there's a tree there, there's a fire hydrant there. And these are actually discrete objects. Whereas raster data actually uses images, the normal image that you have, and breaks that image into small pixels where each pixel represents something. So you can say one pixel is in a water, one pixel is in a campground, and something like that. Triangular irregular networks are very interesting because they represent a network of a mesh network where you can go from one point to another and you can find out spatial attributes. So it's more complicated, but actually storing this in a database is much easier because it has graph theoretic properties and you can very easily store this in a graph database. So if you have worked with Voronoi diagrams or Delaunay triangles, you will be familiar with that, right? One problem to do all this is that the Earth is a round 3D object, and all this mathematics and coordinates, these things work when the Earth is projected to a flat surface. And there you can see that there are many ways to project the data. Some of them are popular. One of them is the Mercator projection, and then you have the azimuthal projection, everything. So no matter how you project the data, you always have to have a trade-off between angle and size. So you'll either get the right angles or you'll get the right size. You will not get both. So if you want to get your hands dirty, I have tried to put together a list of things that you will need. So you need a machine and you need to have data. The data, there's a lot of open data out there. You can take from OpenStreetMap, from the Ontario GeoHub, or even Statistics Canada, or your own company data. And then use a bunch of these tools to crunch through the data. Make sure that you have ready business questions to answer your data. Otherwise, it's pointless, right? For example, where is my customer segment, or how I can predict crime patterns, or how to track a virus, considering what we have today, right? So there are different Docker containers that will either allow you to spin up a PostGIS Docker. A PostGIS is an extension of Postgres. So Postgres has many useful extensions if you have worked with Postgres extensions before. You can also use the GeoPandas library to actually read geospatial data. For example, here I have downloaded 2 sets of data. One is from Toronto neighborhoods, and this is also open data, and one is the Toronto crimes data from the Toronto police website. So I'm trying to find out what are the crime patterns in Toronto, right? And this is the actual data plotted out. These are geodata frames. So just like normal data frames, you have geodata frames, and you can read the data and maintain projections. So 4326 is the projection being used here. That is a Lambert's projection. Also, if you want to create a geospatial table in Postgres, you can use the geometry data type and use OGR to OGR and to insert geospatial data into the database, right? Okay, so what else can we do? So we can do geocoding and joins. This is very important because a lot of times you will not have geospatial data at all. You will just have something that represents geospatial data. For example, a street address or an intersection or something. So that you have to pass to geocoding services to actually get back the coordinates. You can also do the opposite. If you have coordinates, you can get back what is there in that coordinate using these services. That is called reverse geocoding. Okay, so you can use the GeoPy library, which actually sends a rate limited request to these external servers. And here you can see I have printed out I've geocoded 3 random places. I just put in these places and it gave me these coordinates. So these are readily usable coordinates that you can use in your data engineering, right? So how do you actually do the data engineering? So OGC, the Open Geospatial Consortium, has defined these standards. These are called SQL Multimedia Spatial Standards. So MM stands for multimedia. And this gives you a metadata framework based on which you can do all your operations. So you can have, on top level, you have a geometrical data. Then you have these collections and different types of data that is already defined. So no matter what geospatial software you pick up, they will always have this structure. That is why these are interoperable so fast, right? So notice that to find out which areas have the number of crimes, so it's kind of a spatial group by. We are doing a spatial join here with the crimes and the neighborhood data sets, right? And after we do a spatial join, we just group by the data normally to find out which area has what number of crimes, right? So you can either visualize them as a table or you can visualize them as a nice map. So here I represent the data that we downloaded. This is a choropleth map that actually gives you a sense of what are the number of crimes in different neighborhoods, right? So from here you can see a lot of things. We'll look into that. But before that, we have to know how are geometrical joins defined. For a normal table, you can match values. You can do inner join, outer join, and these things. But geometrical data is latitude and longitude. You cannot do inner join and outer join, well, not directly. So this is defined by the 9 intersection model, which actually gives you a specification of how to define geometrical joins. So you can have a line intersecting another line, or a polygon overlapping another polygon. For example, here I have used within, and that is why I'm able to get what are the number of crimes within a particular neighborhood. Okay, so it will do the math internally. These are the functions that are available in PostGIS. So these are Postgres functions that you can directly call onto geometries like crimes and neighborhoods that I've called here. And these joins also have the properties of normal joins like reflexivity and transitivity. So if you have A equal to B equal to C, then A is also equal to C. So those properties also hold here, right? So this is very important, how to be able to join data, because if you don't join data, you cannot enrich the value, right? You need to be able to create geographical features by joining data, right? So isochrone maps, as I said, isochrone maps are very interesting. They're extremely useful. For example, they will help you answer questions as to how many workers are within a 15-minute drive of a particular outage, right? Or how far could this stolen vehicle have gone by now, right? Also, if we put a bus stop here, how many riders will actually use that service, right? So how many riders will live within a 5-minute walk of a bus stop? To answer these kind of questions, you have to make isochrone maps where you choose one point and then you get polygons for as boundaries, right? So the main component of making isochrone maps is the underlying network of roads. The road network will let you know how far you can go using that road, right? So to use and read road networks, you have very good libraries like NetworkX and OSMNX. And suppose you choose one particular crime under investigation, and then you want to know how far could this person have gone from after committing this particular crime in downtown. Okay, so you input the walk mode. You can also give drive or bicycle. Then you create the graph from the point, and based on the time intervals like 15 minutes, 20 minutes, you are supposed to get polygons. So the polygons should represent the extreme boundaries of the time travel map, right? Now, from from the network, from the underlying graph, you will not get boundaries. What you will get are points that represent the extremities of where you can go. So those are the nodes on the graph. But to actually get polygons from point data, you need to use alpha shapes. For example, convex hull is one such alpha shape. So here you can see that although I have colored the points differently, to get the polygons here, I have to get convex hull. But convex hull is just one type of alpha shape. You can have many different types of alpha shape. So you can use the alpha shape library in Python to actually get these polygons. You can see that convex hull is much more inclusive, and what is known as concave hull is not that inclusive. It's more point hugging, right? You can use the PostGIS function available for this. It is called the concave hull function. You can just pass in the target percent, and it will allow you to make polygons from points. There is another extension for PostGIS called PG routing, and you can get driving distance polygons from there, but it is very manually laborious to insert data into this PG routing. So you might as well open up your own Docker service where you can use the routing py library to get these services. So these are all the products that Google uses. Google charges you around 32 USD for every 1,000 of these calls. So if you are finding directions, isochrones, and matrices for 3,000 data, it will be 3,000 multiplied by 3, right? So you can host your own Docker and use routing py to call these services completely. So you do not have to actually go to Google services, although they have very good quality data. So indexes, just like in normal databases, you have SQL indexes that actually index the information. Here also you can index geometrical data. So you can, basically to find out the nearest neighbors of a certain number of points, what you need to do is make an all pairs comparison, right? Which ones are near, which ones are far. It's as simple as that. But in big data, you cannot do an all pairs thing. It's not practical. You will not be able to deploy that solution in production. So what you need to do is index the data in a way that serves your business purpose, right? What are the business purposes that we can have from these indexes? We can query within a range. So we can take one particular crime and say, what are the crimes surrounding that? What are the top 3 crimes that are surrounding that crime? Or we can do spatial joins, as we saw in the previous slide. So we can find out what are the number of crimes in a particular area. Or we can do k nearest neighbors. So what are again the 3 nearest neighbors, right? So to do these kind of things, you have certain data structures. These are quite high level data structures, and a lot of implementations are there. So you can either divide the space into different categories. For example, postal code is a way to spatially index the land that we live on, right? All postal codes are designed in a Z order way. You can also use spatial indexes as ball trees, and geohash is a very new concept which was made about 10 years ago. You can also divide the data. So far we have been talking about dividing the space, but you can also divide the data based on the minimum bounding rectangle, right? Some of the indices that you will find are R3, R plus tree. GIST is a generalized index tree, which is a lossy index, but it's extremely fast. And this is what PostGIS uses underneath. So if you're doing spatial joins in PostGIS, it will be extremely fast. Also be careful that spatial index, if you are making a spatial index, make sure to fit it only on the training data. So when you fit the spatial index, do this only on the training data. If you insert the test data inside the spatial index, then you will have the problem of data leakage, right? Also, these things can be pickled. So what kind of models can you make with it, and how do you go about making these models, right? So to make a model, the first thing you'll need is a spatial weights matrix. A spatial weights matrix is just an adjacency matrix that is being transformed in certain ways, right? So it just proves which ones are the neighbor of what. You can also have a distance-based weight matrix, but that is quite simple. This one is more interesting. So a spatial weights matrix tells you which neighbors are adjacent and which are not. By definition, all spatial weights matrices are sparse. So you can see there is only a 4% connectivity when you are making this particular matrix of Toronto, right? And there are many different kinds of ways to create the spatial matrix. For example, you can use Queen's contiguity, which is more flexible, or you can use Rook's contiguity, which is less flexible. Okay, there are different Python libraries. You can directly plot these things using the dot plot function, and you can see that these distributions, you can also get histograms and distributions using these libraries. So you can just use one geodata frame, run one function, and they'll immediately give you the spatial weight matrix, right? It's as simple as that. There is a lot of material on the internet. You can go and check. But the concept is that it is just trying to encode adjacency in a certain form. So spatial autocorrelation. Spatial autocorrelation is just like temporal autocorrelation in that you have to have some variable and then you have to have a lag of that variable, right? So here we have the number of crimes committed per Toronto neighborhood. And here we have the spatial lag count of those crimes, right? These things you can get by using, again, the library PyCell, which has a lag spatial function to do this. You can see if your analysis is going to be statistically significant or not by doing the Moran scatter plot. So Moran scatter plot will give you the p-norm, which is actually the statistical significance. So the p-value, and if that is less enough, then you can say that this analysis is statistically significant. So what is the result of that? We can use this analysis to identify hot spots, cold spots, and then spatial outliers. Just like we identify 1 standard deviation, 2 standard deviation, and 3 standard deviation and beyond. So this is a spatial distribution of that. So you can do hot spots, cold spots, and then spatial outliers. This is actually a binary representation. This will not give you this so good maps. But there are two types of autocorrelation. There is global autocorrelation, and then there is local autocorrelation. This kind of analysis is usually done using local autocorrelation, because using global autocorrelation, all you can get is the Moran scatter plot, right? Okay, so how to do geo-weighted regression? This is the type of regression that you can use to in your spatial models. There are many softwares to do this actually, but you do not have something in scikit-learn or the PyTorch. You cannot do using those. You have to use some other tools, most of which are written in R actually. But this is a very good tool from the University of Arizona who made this. There are a number of options. It's just like fitting a Gaussian kernel on top of the spatial data, right? And finding out like where are the values clustered, right? So you can either have a non-parallelized version, which is just called GWR, and nowadays you have a modern version, which is both an additive and it can be parallelized, right? So you can see that there are a lot of hyperparameters. These are all hyperparameters of the model. You can use Monte Carlo test. You can use an adaptive kernel, which is like a fixed kernel, or a changing kernel. So you can either make, if the points are very clustered, then you can make the kernel smaller. And if the points are not that clustered, you can make the kernel larger, right? You can also search for the ideal bandwidth and fit a Gaussian or a binomial distribution on that. And if you want, it can also give back confidence intervals for those predictions, right? One thing you have to know is that although there is a fit and a predict API, it is not totally scikit compatible. So you will not be able to do this using scikit-learn. But there are ways in which you can maybe hack a pipeline, but it is not very good. Also, the metric here is not the usual RMSE or the accuracy or the ROC. It's Akaike information criterion with correction. Now, this is a second-order loss estimate that is derived from information theory. So most of these things are coming from information theory, which was developed in the 50s. And this is one of the metrics that is used here. You can also do higher clustering, spatial clustering, One of the state-of-the-art ways of doing that is spatially constrained hierarchical clustering. You can check these out on the internet and you will find a lot of stuff, right? Okay, so now let's move on to a new type of geospatial data, that is images. We know that these images are raster images are there. We also know that satellite always take pictures from of the Earth. So we can download that data and do our analysis. For example, you can see that the download of satellite data has increased has increased like exponentially, right? And these are various sources with which you can use to analyze satellite data. You can sit in your home and do remote sensing analysis, right? These are pretty new projects. You can see that it's detecting ships and then doing feature detection and all these things. So this kind of shares a lot of goals with image processing. For example, you can do image classification. You can classify whether it's a dense crowd or a sparse crowd. You can do object detection. For example, you can find ships and airplanes and like that. You can do semantic segmentation, so you can extract road networks for routing and travel time estimation. And also you can do instance segmentation by extracting buildings and instances of different kinds of objects. For example, Microsoft has a good project going on that will extract buildings from a map, right? So what are the cloud native ways of doing these things? So you have to run these things on the cloud, and that is Kubernetes actually forms a very important part of that. You have to have open data and a lot of community around it to support it. But if you are doing this in open source, please use Kubernetes operators. It is extremely good. I use it every day. Also, please try to use a massively parallel data store, because you need to parallelize the geometrical joins. And sometimes in big data, you have a lot of serialization cost. So if you can somehow save that serialization and do zero copy, it will be really good. There are actually very limited out-of-the-box solutions for spatial modeling and inferencing. So you have to kind of hack the tools, which is why there's a huge proprietary solutions market. These companies make insane amount of money using their products, right? If you're making real-time spatial models, which is actually a part of the hype cycle, so you can see that the hype cycle is predicting that AI and GIS is doing the most amount of contributions, right? So you need to use a lots of GPU. So you need to have a lot of money, right? And if you're using the cloud services, they actually have their pros and cons. While Amazon has very good serverless databases where you can do geospatial joins and all, it does not have that good of a map API, nor it does it give you any geospatial data, right? So it has very good partnerships with S3 and Tableau and all. On the other hand, if you are doing Google Cloud, it has very good data and kind of decent tooling, but not so many good tie-ups and all that. Azure is somewhere in the middle. It has very good market coverage, and their databases also support geospatial data, right? So what are the things that we have learned from here, right? What is the knowledge that we can gain from here? The knowledge that we can gain is that there is a lot of data that is there to explore, right? Because location smart models assumes that proximity explains some variability in the data. Also, that if you have some knowledge of computational geometry, it will reduce your time to insight. So you can go from data to insights in a very short amount of time. Also, if you are making maps and displaying your data to different stakeholders, please maintain very high ethical standards. Otherwise, this is pointless. You will do a lot of damage, trust me. There is a lot of open source projects and file formats that exist and enable you to do regression and classification, but not enough as we might hope. Like you cannot call a scikit-learn or any classic API to do this kind of regression. There is an intersection between deep learning and GIS, and it is helping answer a lot of business questions. Also, if you are using open source and the cloud, please make sure to use Kubernetes and microservices, because it is really cool and reproducible, right? If you want interoperable softwares, you have to work with OGC and ISO standards. Otherwise, you will not create value for your clients and create more technical debt. And so there are a lot of very powerful proprietary tools in the market, but they're actually really expensive, right? Some of the notable mentions that I have missed out or didn't have time is that there is not only outside spatial data, there is also spatial data is also being used for indoor navigation. So you have this new standard from OGC called Indoor GML, where they're mapping out your indoor for warehouses and houses and stuff like that. Also, point clouds are very interesting. It's very colorful, and it will be the thing of the future. Okay. Also, in the world of GDPR and privacy, if you want privacy preserving location applications, you have to use spatial Bloom filters. Please look up on Bloom filters. They're extremely cool. They are kind of a probabilistic data structure, and it's used in a lot of applications. Also, if you have any questions, please feel free to ask me. That was my presentation. I have sent the link of the presentation in the thing. Let me see, somebody is having permission issue. I set it as anyone with the link can view this. Done. Please, can you check again and let me know if you are still having permission issue? Is there a trend away from open source data? I've noticed that some GIS data. Actually, I'll tell you why. This is what we get as data scientists trickles down from military applications. So you will, if you are not working in the military, you will never, or in the government, you will not see 80% of the data. What you see on the website is actually 20 to 30% of the data. So you will always have that problem. Most of the data will be closed source. But more and more data is open right now. Right. Maybe because of the VPN network. Any other questions? Any kind of... So here are my coordinates. If someone wants to look me up using coordinates, and here is the correct projection for these coordinates, right? So as a geospatial scientist, I thought I'd give my coordinates also. Yes. There is a book called Spatial Analysis. There's a book called Spatial Analysis. I don't know who is it written by, but please go through this information. You'll make a lot of nice presentations and a lot of nice models. If you are new to geodata, please use GitHub. GitHub has these geospatial notebooks, which are incredibly useful, right? Don't use books. Books are too classic, right? If you go through books, you'll end up wasting a lot of time. Use YouTube, use Python notebooks, and use GitHub. Thank you. Please get in touch with me if you need more advice. I really didn't have time to explain everything, but I plan to create more workshops in the future because a lot of people are interested in spatial data, right? Yes, please, I will send you the GitHub to the link locations, right? So you can say awesome geospatial learning GitHub. Geospatial learning GitHub. So you can just mention awesome geospatial learning GitHub and you will get the link. I try to put in as much stuff as possible, but yeah, you can only do so much. Thank you. I'm happy that you guys enjoyed the session. So within geospatial data, I am really interested in LIDAR. So I am actually working on some projects which will do autonomous navigation using LIDAR maps. So LIDAR is like the thing of the future. It's totally another dimension, and you need to really check it out. Maps, the use of maps are over. Maps are too old. Yes, point cloud systems, absolutely. So I have some experience making small robots that will actually navigate from one place to another using graph data. But it's really finicky. The tooling is not very good, and you have to write a lot of C++ code. So that it's difficult to do with Python. You have to write a lot of C++ code. You have to know how to work with Arduinos. You have to know how to work with ESP. So those are edge devices, right? SAR imagery. I was actually looking forward for something like that. But yeah, this is on my cards. I'm actually doing a POC on that, but it's kind of for the government, and I don't want to speak about it. It's very difficult to get those things, right? This is the latest kind of data that is available. Aptitude radar. There's a whole, as I said in the learnings, there's a whole new world to explore out there. Like I literally I do research all night, and I always love implementing small projects. I was trying to actually use coronavirus dataset, but it's not available. How big is the government market for GIS? Huge. Government wants to not only own the land, it wants to develop and have picture of the land 20 years ahead. So 20 years from now, how will it look like? They have to map it from now. And that they are actually looking at every piece of land in the entire like boundary, and even not just the land, it's about 120 feet above. So it including, because tomorrow smartphone will be drones, so everybody is going to have a personal drone, and those drones need to also be mapped using geospatial and geofences, right? So everybody will have a geofence around their house. Beyond that, the police or anybody will get an alert. I was actually trying to do this analysis using COVID data. If there are clusters of people getting affected, but there is no point level data of COVID. I think University of Toronto has that data. There is the like flattened.ca, but they are always giving top level aggregates, at least for at the country or at the province level. At the point level, you cannot actually do the analysis. That data is not available. So spatial bloom filters is very interesting, because once you have certain, if you want to not let know, if you have to do some privacy on the location data. So what is the need of a privacy preserving location data? You might have to call from a phone and you do not want to let know where you are, right? It could be a case. In fact, in tomorrow's world, everybody will not want to let know what their location is, right? So in that case, you have to use spatial bloom filters and say whether you are in a particular location or not. What is the probability that you are in a particular location? So it's kind of used to obfuscate and just give you an aggregate view of whether a person is in an area or not. This is an active area of research, actually. I am working with some professors to understand this more. I have not worked in a project with this, but I would like to, if anybody has a good use case. Yes, absolutely. So hold on. So if you use this particular GitHub, you will find a lot of data there, all kinds of geospatial data, satellite data, road data. You can use Statistics Canada. I have looked into all the geospatial data that Statistics Canada has, and it will give you exact like boundaries of County Moon and everything. You can use Ontario GeoHub if you are doing Ontario. And in fact, all of the municipalities, they are having their own like geospatial data infrastructure. So you can use that too. Or you can get in touch with me. I can remember something maybe at that point of time. Right now, there is this is all I remember. Like, there is a lot of data out there. Every day when I have to solve a problem, I go to the internet and look for data. One very good data source is GeoFabric. GeoFabric actually allows you to download the entire planet's map in one pen drive. So within about 100 GB, you can have the entire planet's map. It's also called Planet OSM. So you can use this you can host this in your own. It is absolutely free. You don't have to pay 1 cent for that. And using this, you can also make vector tiles. Vector tiles are what you see in the Google Maps and all mapping applications these days, right? You can also do data science on that map because it gives you some point of interest data, but it's not complete. It's not complete at all. So here you can see some of the data sets that are there. You can use this Landsat data. You can use, if you are doing satellite imagery. Otherwise, you can, for classical sources, you can refer to that GitHub. Great to see you guys, to have interact with you. Really, please get in touch with me any way you can. I would love to talk to you regarding anything about data. See, I don't only work with geospatial data. I work with biological data. I work with real estate data, with telecom, and with financial data. I work with any kinds of data. I'm the data guy. That's a good question. Game changing in the space of use DL in location. Let me look up actually. Let me look up and send it to you. So for classical data, you won't be able to use deep regression. But if you are doing any quantile regression or Bayesian regression, then you need to use deep learning because there are no libraries. You have to do the neural network thing. I will find out something and send over to you. Let me see. So you can have a look at this. This will give you some very good deep learning applications in GIS. Some idea, but this is kind of good enough for now, right? This can get you started. When in doubt, what to do? Always follow S3 because S3 is going to have the top of the line geospatial stuff. They were the first in the private sector business and they are really good. Thank you all. Thank you everybody for attending this session. This was great interacting with you. If you have any more questions, please send me. I have a meeting that I have to attend, unfortunately. But please take care and have a great day and stay safe.